Alrighty, so let's get started with today's lecture. We touched on the idea of exploitation versus exploration at the end of the last lecture, and we're going to flesh out that idea during this lecture, and then we'll spend the rest of it talking about bandit algorithms, which are really at the core of reinforcement learning and how it works, and it's just one of the methods that we can use to solve a reinforcement learning problem. So a bit of a recap from last time. One of the main challenges in reinforcement learning, and I believe in real life as well, is this trade-off between exploitation and exploration. And that trade-off is that in order to obtain lots of reward, we have to prefer actions that produce good results, right? So we take I think the example last time was eating at Wendy's, right? If you're choosing fast food because you know that's pretty decent. But also, you have to actually try new actions in order to see what rewards actions actually produce. And so you must exploit the knowledge that you have, but also explore in order to gain more knowledge about the values of actions. So what is learning then in the reinforcement learning process? Well, learning, in my opinion, is something along the lines of it's the process of gaining new knowledge or modifying existing knowledge to be more accurate. Okay, so you get some new knowledge, and either that's completely new to you, or it's reinforcing some idea or knowledge that you already have. So we've learned something, basically, if it's information that we didn't have already. So even if the knowledge that we're given is the same that we already had, that's actually still learning, because now we know to trust our beliefs with more certainty than before, right? If you've seen one thing produce the results of 100 once versus another thing produce of the results of 100 times in a row, you're probably a lot more certain and trusting of that second thing where you had 100 times in a row. So it doesn't need to be a new value that you're given. Any new knowledge that you're given is learning. So exploitation is exploiting our current knowledge, meaning that we have some values and that we're going to choose the actions that produce the highest values. And so what this is low risk and possibly low reward. We could magically know the best action, so that would be high reward. But typically, this is low risk, low reward, meaning that we're not risking much because we kind of know the value of this action, versus if we explored to find better actions, that's a higher risk because we may be getting lower valued actions in that exploration process. And so exploitation is always choosing actions we're familiar with, and it gives us very little new information. Exploration, on the other hand, is trying actions that we either haven't tried before or have tried less than other actions. So this helps us learn their values over time, and we'll show an example of this. I have a very illustrated example using slot machines, but we'll see this. And it's possible that the new actions we selected have higher rewards than previously selected ones. And so once we've explored sufficiently, we can exploit the best actions and actually know that they are the best actions, right? So if you've tried all 10 actions a million times, you're probably pretty certain at that point of what the best action is. So the example we're going to use here is called the n-armed bandit problem. And the n-armed bandit problem, down here you see an octopus. This is actually a picture from the textbook. And we've got all these different slot machines. And the n-armed bandit problem comes from the old name for slot machines. So old slot machines, you used to have to pull a physical lever. There was no real electronics in them. It was all mechanical. And so they were called the one-armed bandit because they had one arm and they stole all your money, right? So if you have multiple slot machines, that's called the n-armed bandit problem. And the problem is to repeatedly make a choice among n different actions. After each action, you receive a reward from a stationary probability distribution, and we'll talk about that means in a little bit, depending on that action. And the objective is to maximize your total expected reward over a number of action selections. So basically, if I give you $100, or I say you have 100 tries and there's 10 slot machines, how would you pull the levers in the slot machines to maximize your expected reward over time? That is, in essence, the reinforcement learning problem, actually, if we phrase other problems to look like that. Okay, so I actually had a slide on this. The n-armed bandit problem is also called the multi-armed bandit problem, and it comes from slot machines where you have the one-armed bandit as the nickname for the slot machines. And so you have a limited amount of money, and you try and win as much as possible. And so this limited amount of money here, that's not always a perfect analogy to reinforcement learning, but learning takes time, and the limited amount of money analogy here may be a limited amount of time or limited computational resources or whatever. We have some budget that we have to spend in our learning process. And so how do we select which levers to pull? Some slot machines may pay off every time. Some slot machines may never pay off. What is the algorithm that we should use to solve that problem? And this problem is everywhere, right? So in this problem over here, which we'll be doing for assignment 5, you're trying to move in different directions to get toward a goal. So there you've got a 4-armed bandit problem, where the different arms are actually which direction do you head in. Over here, do I stay at the job that I'm currently at, or do I apply for that new job where maybe cooler people work, or maybe I'll get more money, etc. So there's this multi-armed bandit problem comes up everywhere in real life. So for actually computing and implementing in a computer exploitation versus exploration, if we maintain an estimate of action values, at any time, one or more of them is the greatest value, right? So one of them is the greatest value. Maybe we have a tie, but essentially we have one biggest value. That is the greedy action. So the greedy action just means of what I currently believe, this action has the highest value, therefore I want to take that action. So exploitation is choosing the greedy action. And this maximizes single action returns. Exploration, however, is choosing a non-greedy action to improve your action estimates. And so this is required for future reward maximization. And so reinforcement learning methods, at their core, are ways of balancing exploitation and exploration. That's what we're going to do. So in terms of actually implementing this thing in code, there's two very important concepts. One is, how do we store and update the value estimates as we learn over time from new information? So this involves, okay, I have a current belief of the value of all my actions. When I get a new action, or I take a new action and get a new reward, how do I actually update those beliefs over time? And the second problem is, how do I choose which action to do next based on the current value estimate? And this is the exploitation versus exploration problem. So this is storing and updating the estimates. This varies wildly between different reinforcement learning methods. And then choosing which action to do next, that is our exploitation versus exploration. So action value methods are types of methods that store a value and choose an action. And so how do we store the current value estimates of our actions at particular states? So we have this definition here. It is Qt of A. And so Q is going to be our estimate value. Why is it Q? I'm not sure, but that's what the book uses, so we're going to stick with the standard terminology. So Qt of A is our estimate of Q star of A. Q star of A is the actual expected value of A at time step t. So Q means value, T means time step, A means action. So what is the value of A after t time steps? And this is our estimate of that value, because of course we don't know the true value, unless we were somehow given that true value. Q star of A is the actual value of an action, which actual value would mean the mean reward if we did this thing, to infinity. And so as t goes to infinity, Qt of A heads toward Q star of A, right? So if we've done it a bunch of times and we're recording the value of these actions, we get a better and better view of what the true value is going to be. Excuse me. So we're going to do an example and that is the n-armed bandit problem, where Q of A is the estimate of bandit A's reward. So choosing a bandit means I'm going to select slot machine number 3 and pull it, right? And so choosing a bandit is one action. So pulling the lever is one action. How are we going to store our estimates of all those different slot machines? Well, let's use the handy storage device of an array, right? Really high-tech stuff we're going to be doing here. So if we've got n bandits, we're going to have an array of size n, where Q0, so for example, if n equals 4, if we have 4 bandits, before I have started pulling levers, what is my estimate of what those values are, right? Well, I've got to have some estimate there, and so for the time being, let's just set all of those values to 0. So my belief going in is that all of these slot machines are basically, over time, I'm going to break even, right? So I'm going to have a value of 0 for all of these. So Q0 means at time step 0, I have no rewards yet, and this is my belief of the values of all of those things, and it's just 0 for now. After some number of time steps, t, this could be 10, it could be 1,000,000, it could be 100, we're going to have some values that we associate with each of those bandits, okay? So it's going to go from some initial guess to some estimate at time step t. And so let's go through an illustrated example of this, and hopefully this makes it more clear what's actually going on. So this is the problem, and let's first go over what all these things mean. So up here we have our different slot machines. If you're watching this on the video, my face is probably covering up the top right corner, but it just says 4 on it, right? It's a slot machine with 4, so there are 4 different slot machines. And this represents our different actions, okay? So action 1, 2, 3, and 4. Now, if we're storing this in an array, we'd probably use 0, 1, 2, and 3, but you get the idea. Next, we have this thing called a distribution, which I'll talk about in the next slide. We'll leave that for a bit. And then we have the rewards. So as we select slot machines, we're going to pull the lever, and down here, we're going to record the rewards that we get from pulling those levers. And down here, we have our values, which are our estimates of the values of each action after a certain number of time steps. So that's going to be starting at time step 0 and going time step 1, then 2, then 3, then 4, etc. So first, what is this distribution? Well, these different slot machines could be programmed to give money at different rates, okay? So normally, if you have a slot machine and you want to make money, you're going to program them so you make money slowly over time. So in reality, a slot machine is never going to have a positive return value for the user, right? You just go out of business. You're giving away money. So in reality, all of an actual slot machine that you would find in a casino would probably say something like, okay, every hour we're going to be making the user lose $10 or something like that. And if you actually, if you go to Las Vegas has like a gambling commission that actually sets the rates that you're allowed to have on slot machines. So there's a legal amount of money that you're allowed to take from users every so often or however many spins. And so I think if you're actually in a regulated area, you can probably look up the rate at which you'll lose money, and still people play these games, right? So, but gambling addiction is a real thing. You get people buying loot boxes and stuff in video games. It's the same thing. So this distribution means what is the rate at which these things are returning rewards. So I've just come up with a few examples here to make this less monotonous. So for example, whenever we pull the lever for slot machine number 1, it's always going to give us 5. That's just what's going to happen. It's going to be 5 every time. This one is going to return -20 or 20. This one is going to return a random amount between 0 and 10. And this one is going to return a random amount between -10 and 10. So just hand up and tell me which slot machine you would play if you were given the distributions here. Yep.
The first one.
Okay, so you're always getting 5 back. It's a good answer. Yep.
3, because 50% of the time you get still always be positive.
Okay. Any other? Would anyone have chosen anything differently? Yep.
Number 2.
Okay, so you're a gambler at heart. Why would you choose number 2?
Go big or go home.
Go big or go home. Okay, so we got a gambler in the house. Okay. So if we did do the math, if we were to pull these like an infinite number of times, what we're interested in solving is the problem of expected value, right? So averaging maybe all of these over time. So if we average always 5, easy, you're averaging 5 per spin. Negative 20 or 20, if you average those, you're getting 0 per spin over time. Random 0 to 10, you're also getting 5, right? Because that's the median value between these. And random negative 10 to 10, well, even though you could get any possible value, over time, you're breaking even with this one as well. And so I've got 2 that have 5 and 2 that break even, just to show that, you know, we could have any distribution here. All right. Down here, we've got Q0. That is our belief at time step 0. So how do we choose those initial Q values? It's possible sometimes that you may have some information, right? Someone has told you from a previous learning session, here were my estimates. Maybe you should start at those estimates. But most of the time, if we don't have that sort of thing, what we're going to do is just, say, choose 0. Okay? So Q0 of 1, that's going to be here. Q0 of 2, Q0 of 3, Q0 of 4, and all of those values are going to be equal to 0. So Q0 means our initial estimates before any rewards have been given. Now, we're going to start getting rewards, but how do we want to update our rewards as we get new rewards? Well, 2 ways we're going to explore in this course, and you know, the way mathematics works is that there's a lot of different ways that you could do this, but we're only going to look at a finite subset of those. So the first one is the sample average estimation, and we've already sort of alluded to this. So QT of A, sample average estimation. So the natural way of calculating QT of A, so our guess of the value of A at time step t, is to just average the reward we've received so far after however many times we've played that particular slot machine. That's pretty intuitive. So at play T, action A has been chosen Ka times. So K here represents the number of pulls of the slot machine. And after T time steps, we have Ka pulls of that slot machine. So if we have rewards R1, R2, all the way up to RKA, then, scary formula here, our estimate of the value of A is the summation of all the rewards we gotten divided by the number of times we played the slot machine. Okay? So R1, R2, those are just the rewards that we've gotten, and then Ka is the number of times we played it. So this is literally just the formula for an average. And if Ka is 0, then we would have, you know, a seg fault here. We can't divide by 0. And so we define Qt as some initial value. For example, if t is 0, then Qt of A is equal to 0. And the idea here is that as Ka gets large, as we sample a particular slot machine more and more and more, Qt of A converges to Q star of A. Because, you know, the law of averages, as we keep doing it more and more, we get closer to the actual distribution. And so since we're taking the average of samples, this is the sample average method. Very, very clever title, right? So let's start pulling some slot machines. And we're just going to go left to right. Doesn't really matter what order we pull them in. So I'm going to choose action number 1, and I'm going to go left to right. And so what we've gotten is we pulled this one, surprise, surprise, we got a 5. Because it always gives us a 5. So now we're at time step 1 because we've taken one action, and I've updated Qt of A to be the average of everything in this column. So the average of 5 is 5. We've gotten 5. Ka is 1 for action number 1, so 5 divided by 1 is 5. Now we're going to pull this one. We pull this one, we get minus 20, so our average is minus 20. We can see that this is now Q2. So Q2 of 4 is still 0. T is the total number of actions that we've taken, not the number of times that we've chosen the individual action. Ka for A4 would be 0 at this point because we haven't pulled action 4 yet. Next, we'll pull this one. We could have gotten anything between 0 and 10. We got a little bit unlucky, and we got a 4. So we get a 4 here. And now we pull this one. We get super lucky, and we have an 8. So our update is for 8. Now we'll go back to the left, and we'll choose everything one more time, just for completeness sake. Surprise, surprise, I got a 5 again over here. So my average is 5 plus 5 divided by 2, which is still 5. Here I've gotten a 20. So negative 20 plus 20, that's 0 divided by 2 is 20. Over here, I've gotten super unlucky, and so I got a 0, so I average 4 and 0, which is a 2. And over here, I've gotten a negative 2, and so 8 plus negative 2 is 6. 6 divided by 2 is 3. And so Q8, I could ask you on an exam. I give you everything except the bottom row, and you have to fill it out. Okay, so it's a calculation. Calculations done in the slides are pretty good exam questions normally. And there is another method, which we will be using in a little bit. I could tell you, okay, if these are the rewards that we got, using this method, show me what Q8 is, for example. So down here we can see that, all right, this one, I don't know the distribution of this one, but I'm pretty sure that 5 is a good estimate of this one, right? Because I've only gotten 5s. Here, there's a wild variance between these, but my current estimate is pretty accurate. Here we can see that, okay, the actual expected value from this one is going to be 5, but my value here, I got unlucky with a couple of spins, and so this is lower than average. And here, we got kind of lucky so far, and so this is a little bit above that average of 0. And so you can imagine how over time, as we do this an infinite amount of times, when we have Q a million down here, these will probably be very close to the actual expected values that we calculated by hand a minute ago. Okay? So any questions about this so far? I think it's pretty intuitive. It's just this is a Bandit method, and so this is how you update the values after you get the rewards. Next, we're going to talk about the incremental update estimation. Before I go on here, who can tell me, with a hand up first, if I wanted Q a billion or Q a trillion, what's going to be problematic with that calculation here? Yep.
Adding a trillion times.
Yeah. So not only adding a trillion times, but keeping track of a trillion things. Right? I'm going to have this. How am I going to write that down? Do you have, I was about to say a trilobyte, a terabyte of RAM that you can use? Maybe you do. I don't know. But keeping track of all of that is super annoying. And not only that, but every time we pull a new lever, it's going to take longer and longer to do the calculation. Right? Because at first, I only had to average one number, but now I'm going to have to average like 250 million numbers or something. And it might take a few seconds to do the update when I don't want that. So the incremental update estimation is a method that is going to help solve that problem. Okay, so the incremental action value estimate. I'll take a quick drink here. Let's remember that our average formula, QT of A, was just to sum up everything and divide by the number of things. So that was pretty easy. However, as I just said, in order to do this, we need to store all the rewards, and that's going to be bad. The problem here is that the memory and computational requirements grow over time if we have to store a list of all the rewards that we got. And so what we're going to do is we're going to do a little bit of math and derive an incremental formula so that memory is no longer an issue when calculating these values. So what we have is that our new average after we get a new reward is equal to a function of the history of all the samples. And that history could be quite large. And if you're doing reinforcement learning in a computer, typically it will be very, very, very large. What we want is that the new average is equal to a function of just the old average and the new sample. We don't want to have to store that whole thing. So let's look at this. I know this text is a little bit small. Hopefully you can all read that and follow along. So this is just the same formula where we have qk is equal to the sum of all the rewards divided by k. So what we're going to do is we're going to change this into a little more convenient way of representing it by putting in its summation form, right? So hopefully you all know what the summation form is. So sigma here, summation from I equals 1 to k of rk, and then divide that by k. So this is the exact same thing we have here, from 1 to k of ri divided by k. So if we want the formula for qk plus 1, we can just change this formula and sub in k plus 1 where we had k, right? So this is the formula for qk plus 1. Instead of dividing by k, we divide by k plus 1, and instead of summing to k, we sum to k plus 1. So that's just adding the next thing. Pretty easy so far. What do we do next? Well, we're going to split this into two terms. So now comes the tricky math part. Not tricky insofar that you can't understand it, but you have to manipulate this in a way to get to a desired final result. So what I wanted on the last slide here was that I want the new average, this is qk plus 1, right? I want that to be a function of the old average. So what I have to do here is get qk onto the right-hand side somehow. So let's take this, and if we look at the summation from I equals 1 to k plus 1, that's equivalent to the summation from I equals 1 to k plus the individual term for k plus 1. So that's step number 1. But if I look over here, what this is, so this is the summation of I equals 1 to k of ri, and look, this is the summation of r equals 1 to k of ri. But that's divided by k. So if we multiply this by k, this is k times qk, right? So up here, if you look, qk was equal to this term divided by k. And so this without the division by k must be equal to k times qk. So now we've got what we wanted. We've taken this big summation out of here, where we had to sum up all of those rewards, and all we have now on this side is qk. So now I can do it in terms of the previous update. But I want this in a nicer form, so let's keep going till we get that nicer form. So what we're going to do now is we're going to, inside here, let's just rearrange these terms. So we'll reverse these terms, but that's okay because it's a summation. And then I'm going to add a qk and subtract a qk. And overall, that does nothing, right? It just adds 0, so that's fine. But this is going to let us put this into a little bit of a nicer form. So down here, what we'll have now is this rk plus 1. Then we're going to take these two terms, which is k times qk plus 1 times qk. And now we have k plus 1 times qk. All right? And what this will allow us to do is the following. Now, we can bring this qk outside, because if we have divided by k plus 1 over here and multiplied by k plus 1 here, those two cancel out, so I can bring the qk outside. See how that works? So we have qk plus 1 over k plus 1 times rk plus 1 minus qk. So what does this mean? It means that my new estimate, whenever I pull a new reward, is equal to the old estimate plus 1 over k plus 1 times the new reward that I've just gotten minus the old reward. And so this is how you do averages without having to keep the list of all the rewards that you've gotten so far. And this doesn't just work for rewards, of course. It will work for any scenario where you want to average something. So this is called the incremental implementation because you don't need to store the history. You can just increment it every time you get a new reward. So qk is the average of the first k rewards. Then qk plus 1 is this, which is now equal to this that we just derived. And so we have the form that we want, where our new estimate of qk plus 1 is equal to the old estimate of qk plus some step size, which we'll talk about in a second, times the new sample, rk plus 1, that's the new reward that we just got, the new pull of the slot machine, minus the old estimate. And we refer to this value right here, the new sample, as the target value. The reason that's called the target value is because I've just gotten a new sample, and I want to trust that new sample somehow. And so I'm taking my current estimate and now I've got a new estimate, and my old estimate is going to go toward the new sample. So for example, if my current belief is 0, and I've gotten a value of 100, I should move from 0 toward 100 somehow, right? So that is the incremental update for averages. However, I mentioned before, and it was just kind of a passing remark, that this is for static distributions. A static distribution means it will never change. What happens if the distributions change dramatically? What do I mean by that? So let's say that I'm pulling this slot machine, which is always 5, right? I've pulled it 1,000,000 times, so I've gotten 1,000,000 5s. I'm very, very certain that it's a 5. My average is exactly 5, right? Because it's 5,000,000 divided by 1,000,000. Jesus, what am I? Yeah, thank you for doing that math for me. Just a brain fart. But what happens is if distributions are allowed to change. If after 1,000,000 pulls, I start getting 100, or let's say negative 100, right? So I've pulled 1,000,000 5s in a row, and then I get negative 100, negative 100, negative 100. If you're using the average, if you get 3 negative 100s after 1,000,000 5s, what's your new average? It's 5-ish, right? It'll take 1,000,000 more pulls to get you away from this average. So, do we want that, right? Maybe in some cases we do, but it's probably not in the case of reinforcement learning, because our environment could be dynamic. The rewards that we get from doing actions at particular states could change over time. Maybe the stove that was really hot is now turned off, and it's cold, right? I don't know why you just want to touch stoves randomly, but we should update our belief at how good that action is, regardless of the morality behind it. So what we want to try and do is say, okay, the average is treating every single reward that we've ever gotten with equal trust. But in the real world, it's probably true that the things that have happened more recently should probably be trusted a little bit more than the things that have happened in the past, because things can change, right? So let's have a look at that. If distributions remain the same, the problem is called stationary. If distributions are allowed to change over time, it's called non-stationary. So imagine this problem where we have an average of 1 for 1,000,000 time steps, and we change to 100. The average would not update for a long, long time. So we still want to use this incremental update idea, where we don't have to store a list of all the averages, or a list of all the rewards that we've gotten. But we want to change this averaging formula. So averaging works fine for stationary rewards, but not if our rewards can change over time. So we want to weight recent rewards more than old ones in case the values change, or the distributions change. So what we're going to do is we're going to use a constant step size parameter, alpha, between 0 and 1. So if we look back at our old formula, our alpha value here changed. So every time we got a new sample, we trusted a little bit less and less and less and less, because it has to be, with respect to all the others, the same trust, right? But what we're going to do is say now, we're going to have this alpha, we're going to fix it. And what will happen if we do this? So we'll get our new value is equal to the old estimate, or our new estimate is equal to the old estimate plus alpha times the new reward minus our previous value. So let's just have a look at that. So I'll do the math, and then I'll also give an illustrated example. So here's the formula that we have. The new estimate is going to essentially be pulled toward the new reward by alpha. And just as a quick spoiler, if my old estimate was here, and my new estimate is here, alpha, if it's 1, goes all the way to this one. If it's 0, stays at the old one. And if it's in between, that's how far we go. So if alpha is 0.5, if this was our belief and this is the new reward, we go halfway. Okay, so that's what's going to happen with this math. So let's do an example. If our previous estimate was 50 and alpha is equal to 1, meaning we're going to go all the way to the new reward, and our new reward is 100. Well, how does the math work out? Well, we've got 50 plus 1 times, this is the new reward, minus 50, right? 100, which is the new reward, minus our previous belief, which was 50. And so this is equal to 50 plus 50, which is equal to 100. So what about if we have alpha equal to 0.5? Well, it works out like this. We have 50 plus half times 50. And so this is 75. So in an illustrated way, if we have our QK currently at 50 down here, and then we have a new reward of 100, and our alpha is equal to 1, then it pulls it all the way from 50 to 100. That's what this alpha does in this example. And our new k plus 1 is going to be equal to 100. But if we had alpha equal to 0.5 and our QK was at 50, then our new reward is 100. We have alpha, which pulls it there, but it's only halfway because it's 0.5, so our new value is 75. Okay? And the job here is to basically choose a value of alpha that makes sense for this. So if you really trust new rewards, high value of alpha. If you really don't trust new rewards, or you want to be sure that new rewards are giving you the right value, have a lower value of alpha. And this value of alpha is called the learning rate, typically. So if you ever are doing some learning and they want you to put in a learning rate value, a learning rate of 1 just says whatever the newest reward is, that's what I believe it is. A learning rate of 0 means we never change our mind, and so you never learn. And a learning rate of 1/2 means let's go halfway, right? So the good thing about a learning rate of half would be that, okay, we very quickly go half, 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 half. We get toward that value, right? But now, if we get a really unlucky value, well, we go halfway toward the unlucky value. So in practice, what I've seen most often is an alpha of around, for this particular formula, between 0.1 and 0.01, meaning that we learn kind of slowly. We only go 10% of the way toward the target each time. But if we do get one of these unlucky values, we don't go all the way towards that unlucky value. Okay, so lower learning rates are typically used. And some of these newfangled deep reinforcement learning algorithms have learning rates of like 1,000th or something crazy. But just keep in mind that that's what the value means. And these two methods are by no means the only methods, but they're the only ones that we're going to be looking at for now. Actually, we will look at another one at the end of the lecture. So these three. So for the incremental update, let's do the same example now, but for the incremental update instead of the average update. So here, we are going to get a reward of 5. And so our previous, and our alpha here is 0.5. And so that means that every time we get a reward, we go halfway between our previous reward and the new reward. And the issue now is that the order in which we receive rewards matters. Okay? If we were at 0, if we got negative 100 and then positive 100, we're going to get a different value than if we got positive 100 and negative 100. Because it's going to trust the more recent thing a little bit more than the previous things. And we'll show an example of this. So we get minus 20 here. We're going to get the same rewards as we did last time. So halfway between 0 and minus 20 is minus 10. Over here we get 4. Halfway between 0 and 4 is 2. We got 8 here again. Halfway between 0 and 8 is 4. Now we get our new rewards. 5. Halfway between 2.5 and 5 is 3.75. Now we get a 20. Halfway between negative 20 and 20 is 5. We get a 0. So halfway between 2 and 0 is 1. And we get a negative 2. Halfway between, 4 and negative 2 is 1. So the difference is that we have 3.5, 3.75, 5, 1, and 1. But the averages were these. Okay? So just keep in mind that if you absolutely know for certain that you have a stationary distribution, then you probably do want to use the average update because it'll be a little bit more accurate, right? Because you see here, this is not averaging these two values. This is factoring in the fact that we got the 20 more recently, and we trust the 20 a little bit more. So that's why it's pulling it more toward the 20, right? And if we had gotten the 20 first and the negative 20 more recently, we'd have a negative 5 here. So that negative value would be trusted more. So these are the difference. So on the exam, I could give you this, and I could give you the rewards. And the rewards, I would say something like, okay, rewards are obtained from top to bottom. And so it doesn't matter in like what order we do the columns. It just matters what order we do the calculations within each column. All right, so this calculation shouldn't be too hard for you on an exam. And if I did give it to you on an exam, I would make all the answers integers just to make it a little bit easier. So yeah, those are the two. This is the incremental update with a fixed step size alpha. This is the, and then this is the values we would have for the update, for the average. And keep in mind that we could do the incremental average, and we'd come up with the exact same values here with the incremental average as well. So these are the ways that the banded selection methods are going to take in rewards and update their values of the beliefs of those rewards, or beliefs of the values of those particular actions. Next, we have action selection methods. So at some time, we've got some beliefs. So which action do we choose to do next, right? So we've done number 1 on that slide, which was how do we keep track of our values over time. We've been given some actions, but if we had to select the actions for ourselves, how would we actually choose which action to do? And so we've already talked about the easiest method, which was just to select the greedy action, right? So we take the highest number and we select that one. But as we saw, depending if we get lucky or unlucky or whatever, just choosing the highest number may not be the best thing to do. So on play T, take a greedy action, A star. I regret choosing A star, but it's the best action, right? We use star to denote the best action. This is not the A star algorithm, that's a capital A. But QT of A star is equal to max A QT of A. So what does this mean? It means that for every possible action A of our beliefs at time step T, we take the maximum one. Okay? So QT of A star is just the value of the maximum action at any particular time. So this method always exploits current knowledge to maximize immediate reward. No sampling or exploration to determine values of any other action to see if any of them may be better. And here's a bad thing that can happen by just using the greedy action selection. If we do our example of time step 1, where we got a reward of 5, right here, all of these, we've chosen 0 as our initial value estimate, right? So if all we do is get a 5 and keep pulling that one, because that's the greedy one, it will always be 5, and we'll always keep pulling it, because these never get updated. This one over here could be always pick 1,000, but we'd never know because we never pulled it, right? So the point here, now in practice, what you'll see sometimes is in order to alleviate this a little bit, they'll just say, okay, first thing you do is pick each action once, right? Sometimes you can do that, but that's a little bit of a hack that we're not necessarily going to do. How would you select other actions if you don't want to always do the greedy action? Anyone have an example? What might you do?
Maybe do it like stochastically, so I have a chance to choose the other ones.
Sure. So let's choose a random action, right? So to add exploration, choose a random action with a small probability, or it could be a big probability. Whatever probability, that is called epsilon. So what we're going to do is, in the limit, even though we may only be choosing a random action like 10% of the time, if we do this a trillion times, we're eventually going to explore everything, right? So in the limit, as the number of plays increases, each action will be sampled infinite times. This guarantees that as Ka tends towards infinity, Qt of A converges towards Q star of A which is the best value. So we know that if we are selecting random actions, even if we don't select them too often, if we play enough times, we will get the true averages. In theory, this works, but in practice, it may take a very, very long time to converge, meaning that actually get toward the averages. So over here, in this one, maybe we pull this one first, but we'll have a random action chosen with probability epsilon. And if we choose a random action with probability epsilon, it means that the greedy action will be chosen with probability 1 minus epsilon. So let's say we want to choose a random action 10% of the time, right? So epsilon is 0.1. If a random action is being chosen 10% of the time, it means we're choosing the greedy action. How often? 90% of the time. 1 minus 0.1, right? So it's 1 minus 0.1 or 100 minus the percentage. So over time, even with just a 10% chance, if I did this a million times, I'd still be pulling these like 100,000 times each, right? So that's good enough. And what we're doing here is we are pulling more often the slot machine that I think is best. We're still doing that, but we're exploring. So if we find a new best, we start pulling the new best one, but we're still exploring, right? So this balances exploitation and exploration by just choosing random things. And an interesting thing happens here. So what this is, it's a graph of the average reward over time that we get from pulling these slot machines if we have, let's say, 10 slot machines. Okay? So this blue line here, which is impossible to read for you, probably, but this is with an epsilon of 0. So this is just pulling the same value over time. So what happens here is we keep pulling the greedy action, but it never really changes, so we completely stagnate and we never learn anything new. Next, we have this green line, which is 0.1, meaning choose a random action 10% of the time. And what we see, generally, is that we learn pretty quickly by choosing 10% random things, the value. So we start sampling really quickly from other places. We learn those pretty quickly, and we get to a certain point, and then we plateau again. So with 10%, we learn pretty quickly, but then we plateau. But if we see this red line, this is a 1% random selection. So what happens is, with 1%, we're exploring 1/10 of the 10%. So we learn more slowly, right? We're exploring less, so we learn more slowly. But the cool thing is, once we've learned, we're doing less random things. If you're still doing 10% random things up here, then eventually you're going to plateau at how much reward you're actually getting. Okay? This one is a bit of a better graph to illustrate this, which is the percent of the amount of times that we're choosing the optimal action. So let's pretend here that we have 10 actions. Okay? So we have 10 actions, and we have one of those 10 actions is going to be the optimal one. And so how many times are we getting the optimal action? So down here, if we have an epsilon of 0, we're never actually exploring. So sometimes we could be pulling the optimal action, sometimes we couldn't. This line is probably more like going to be down here. I'm actually not sure why it's up here. But this is straight from the book, so you can go read from the book if you want. The point here is the difference between the green and the red lines. So the green line here is 10% exploration, right? So 10% exploration. We learn over time which action that we want to do, but because we're still exploring 10% of the time, this green line is going to be plateauing at 0.9. Why? Because if we're exploring, doing a random action 10% of the time, then the most we could ever be choosing the optimal action is 90% of the time, right? Versus this red line here, which is saying do 1% for epsilon, 1% exploration. What will happen here is it takes much longer to learn, maybe 10 times longer as 0.1, but once we have learned, it will only be doing random actions 1% of the time. So we might get to 99% the correct action eventually with this one. So the the exploration rate affects how you do this. And so what's done in practice sometimes is that epsilon changes to go down slightly over time. So we might start with a really high value of epsilon to do a bunch of exploration, right? We maybe even had 1 for epsilon at the beginning. Just do random actions to collect some samples. And then slowly over time, as we learn more and more, we're more sure about the estimates that we've gotten, and so we want to explore less, and so we do less things over time. So typically, we do that where we decrease epsilon if we're in a stationary distribution problem, because if it's a stationary distribution, we can be pretty sure about the things we have learned being like the stuff that we've learned is still going to be true forever. But if we're in a non-stationary distribution, then we probably don't want to decrease epsilon over time, because if the values of those slot machines change, we still want to have those exploration values be high. So hopefully that makes a little bit of sense. So the Bandit algorithm implementation looks something like this. First, we choose our value update method, and there's a bunch of them. We just looked at 2 of them, right? So we could choose the non-incremental average formula, we could choose the incremental average formula, or we could choose the incremental formula with the fixed size alpha. We choose how we are going to do that. Then we choose our action selection method. Are we going to use greedy? Are we going to use epsilon greedy? Are we going to use something more clever that people have come up with? Then, once we've chosen these 2, we are going to repeat forever, or until we've run out of training. Choose an action to perform, do the action, so you get your reward from the bandit, and then you update your value from the action. And once your values have been updated, then you choose a new action to perform. We get the reward from the bandit, and then we update our values. And so it's action update, or value update, action selection. Value update, action selection. Value update, action selection. This is the training phase of reinforcement learning, and this is how reinforcement learning actually does its learning. So for example, if you want the pseudocode for the incremental average formula and epsilon greedy action selection, so those are the 2 choices that we've made. Here's our function, which is, so we have bandit algorithm, and this takes in as a function the bandits, right? So this is kind of like your environment. This is the distribution over the bandits. So we're initially going to have our Q value, and let's just set that equal to a number of zeros, which is the bandit size. So that's our Q array that was at the bottom of our slot machine example. Then, because we're doing the incremental average, we need to have that K value. So what I had for K, this is going to be N. So this is zeros of bandit size, and this N is just essentially going to store how many times I've chosen that action. And that's something that I need to have in order to compute the average. Next, while true, this would, of course, in your thing, there'd be some stopping condition, like while I'm not out of Amazon credits or whatever. Set our action equal to null. If a random value between 0 and 1 is less than epsilon, then our action is going to be a random action. So you looked at this for assignment 4, right? So if epsilon is 0.1, that means 10%, then I generate a random number between 0 and 1. If that's less than epsilon, that will happen 10% of the time. So that's how we're doing that. So my action is a random action. Otherwise, my action is the action which maximizes QA. So we're going to look over all the values of Q, find the one that's biggest, and if there's a tie, just choose a random one from that. So we find the action which maximizes Q of A. Then, once we have the action that we want to select, our reward that we get from doing that action is we take the bandits, we look up the action that we did, and we say get value, right? So treat our bandits, all of our slot machines are in an array, and they all have a function on it called get value, and we just get that value. I guess that could be get reward. Get reward would be a more accurate way of saying that. And then we are going to increment the number of times that we have chosen this bandit, so we increase n. And then we do our incremental average update formula, which is just the new value. So the new value, which will be stored in QA, is going to be equal to the old QA plus 1 divided by the number of times we've chosen A times the reward minus Q of A. Okay? And if we wanted to do, instead of incremental average, we wanted to use incremental with a fixed size update of alpha, then down here where we do 1.0 minus n, this would just be alpha. And then we wouldn't need n anymore. So anything involving n we wouldn't need if we wanted that one. The last thing I'm going to say today is this is another way of choosing values. This is called the upper confidence bound. And so the issue is that exploration is needed because there is uncertainty about the accuracy of action value estimates. If we knew that we were certain about our values, then we could just do greedy. If I'm certain this is the best, then always choose the best. But there's uncertainty in my values. Greedy looks good now, but it might not be the best overall once I've had some time to learn. Epsilon greedy explores, which is great, but it explores randomly. And when have you ever thought in life that taking random actions was good? Right? So while epsilon greedy, yes, it does explore, it explores randomly. And so wouldn't it be better if we could select among the non-greedy actions that may be close to optimal with some measure for how certain we are about their values? And so the UCB selection method does this. And here's the formula for UCB, which is unfortunately going to be behind my face on the video. But if you're watching the video, just open the slides and look at that. So 1 second. Let's see if I can fix this. All right. There's the formula. Take a screenshot. Sorry, that's all I can do. All right. When I do the video editing, it's like insanely difficult for me to have it off at certain parts. I just have like a command line thing that takes it from one video and sticks it in the other, so we're just going to have to deal with that. All right, so here's the formula. And it says the action that we want to take at time t is the action which maximizes this formula. So argmax, the maximum argument, meaning that if we take all of our actions and we plug it into this formula and get a value, it's the action that maximizes that value, right? So it says qt of a, that's our current estimate, plus c, which is going to be a constant, times the square root of the natural log of t divided by the number of times we've done action A. What in the hell is it talking about? Okay, let's go through it turn by turn. ln of t is the natural log of t, right? So it basically takes t and makes it smaller. And that helps us handle something. So it's not quite a linear relationship anymore. It peters it off so that it's a logarithmic value based on t. nt of a is the number of times that action A was selected. C is a constant, which if we look, it gets multiplied by this. So if we want to explore more, we can increase this constant. If we want to explore less, we can reduce this constant. So it gives us a little knob that we can turn. Typically what we do is we have all the values that are tried once first, and then the square root term, if you've done any statistics, if we talk about variance, which is uncertainty, there's a square root in there. So that takes that as a measure of uncertainty of the values estimates. And so what the function does is it calculates a sort of upper bound on the possible true value for an action of A. And what this term over here represents is the uncertainty. Why does it represent uncertainty? It's because as nt of A increases, right, meaning nt of A, that's the number of times that we've pulled a particular slot machine. So if we keep pulling a particular slot machine more and more and more, our uncertainty about its value goes down, right? But if t increases, meaning the total number of slot machines that we've played goes up, but not the number of times that we've played this slot machine, then relatively our uncertainty goes up. What does that mean? It means that, let's say, I have pulled 200 total slot machines. Let's say I have 4 slot machines, like 4 actual machines, but I've made 200 total pulls, right? Now, if one of them I've pulled 100 times, I'm pretty certain about its value relative to the others, right? Because half of my total pulls have been that one. So what I should probably do is look at a different one. So what this is saying is, now in that same example, let's say I pulled slot machine number 2 100 times, but I have 1,000,000 total pulls, right? So if I've pulled 1,000,000 total times out of 4, and this one only has 100, then relatively to the others, I'm very uncertain about this one, because they've got like hundreds of thousands of pulls. So what this does is it takes the total number of pulls and divides by the number of pulls that we have of this particular slot machine. And so as we pull a particular slot machine more and more, comparatively to the total number of pulls, our uncertainty value goes down, right? And then we take the square root of that, and then we add that to our value. So what happens is, it is a formula which mixes the value estimate, which is QT of A, with an uncertainty value that we have, which you can think of as like a proportional percentage of the number of total throws, or the number of total pulls in comparison to the number of times I've pulled this one. And if we want to explore never, we change this C value to 0, because then all we're looking at is QT of A. And if we want to only explore, we can change this value super high. So in my usage of UCB over the years, some value between like 1 and 2 or something like that is what I've used for the value of C, and it nicely balances this like QT of A and this. But based on the rewards that you're getting, right, if QT of A, if your rewards in your system are like thousands, right, so I get 1,000 reward from this, 1,000 reward for that, versus in another one, your rewards are like, I have a value of 2 for this and a value of 3 for that, then you're going to need to adjust this value of C to do that. Just give me 1 second with the questions. I just want to go to the next slide. And so what this does over time is that it dynamically adjusts this value based on our uncertainty of values rather than just picking random things. However, what we see is if you have a lot of time to learn, UCB will outperform epsilon greedy. But if you don't have much time to learn, it's still like, okay, I should probably do epsilon greedy. So all of this stuff, there's like the theoretical best thing to do if you have infinite time, right? UCB is really, really good at that. It's actually like provably the best or something. Okay, I shouldn't say that. It's provably really good if you have infinite throws or infinite pulls, but not if you have like a very, very limited number of pulls. Is there a, yeah?
Wouldn't it not really work for dynamically changing distributions though?
Why is that?
Because it's like, if it changes drastically, then like, no matter how many pulls you had, it's completely different, so the rest of the information is irrelevant.
This factors in the value, and so if the system is dynamically changing, we don't necessarily know where it's dynamically changing. So it could be any of them that are dynamically changing. And so what we want to do is, even though it's dynamically changing, we still want to be pulling the one that we think is best quite often, but maybe that has changed, right? So this is how you choose the action, but not how you do the value update, right? So the value update step of that like incremental alpha value update, that is separate from this. This is just the action selection part. Yeah. Was there a question over here? Yeah.
NT of A is basically the K that we saw.
Yeah.
Right?
Yeah. So this value of NT of A, that's just like I copied and pasted this from the book.
Okay.
So that's, yeah.
Another question is about the epsilon. If the epsilon is like 0.9, then the graph of percentage of optimal solution would plateau at 0.1, right?
Pretty much.
Yeah, so in that case, we can say that like exploration and exploitation are both important, but exploitation has to be more than exploration, right?
I'm not going to say that that's necessarily true, but I don't want to say one is more important. I don't think that's the right value. I think that if you're choosing random actions, you want to do so quite infrequently, like typically less than half.
So random action is exploration, right?
Yeah, so I want to do something that I haven't done before. Before you go, I do have just a couple of more slides. And so we've looked at Q of A, which is the value of doing A. What we will see most often is Q of SA. and this is the value of doing an action at a state. Okay? So Q of A is the value of doing action A. That's really only useful in that case where I basically have one state, which is I'm in a casino and I have n slot machines, right? But the value of doing a specific action will vary depending on the state at which it was issued. Meaning, for example, if we're in a maze or something like that, moving up is good if the goal is up. But if I'm in another state above the goal, then I don't want to move up. So my value of moving up depends on the state that I'm in, right? So Qs of A is the value of doing action A at state S. And so what we're going to do eventually for the assignment is we're going to store for each state our action values. And then if we want to know which action to do at each state, we look up the action values for each state. So you're all familiar with this diagram by now. So in assignment 5, we'll be doing more moving around a grid world. I know it's a bit monotonous, but it's a good example, right? And so I want to give you the best example with the most easiest implementation stuff. So what this is, you can look at this. You're at a state with a particular number of actions. And so these are your n actions that you can do. So I'm at a given state. This is action 0, action 1, action 2, action 3. And these are basically 4 different slot machines, right? So at each state, we are doing an n-armed bandit problem. So at each state, we're holding Q values. And then this would be, if we are at state S, if we are moving up and we want to keep our estimates of moving up, that is Qs of 0, then Qs of 1, Qs of 2, Qs of 3. Okay? So just keep in mind that the example we did all class was just, okay, I have n actions. But in reality, when we have real problems, we have n actions at each state, and the value of each action at each state can be different because it has a different context. So possible exam questions on these slides. The formula for the average and incremental update, be able to do the examples we did in the slides. Exploitation versus exploration, what does that mean? So be able to regurgitate that definition or your example of exploitation versus exploration. I might ask for a real-world example of that. Action selection methods, so we've talked about greedy, epsilon greedy, and UCB. I will not ask you to regurgitate the formula for UCB, but I may ask you a theoretical question about what UCB is doing. What happens as epsilon goes up or as it goes down, and what does that mean for things like, hey, can I actually, how often can I get the maximum value if I'm exploring this much, etc. And of course, the pseudocode for the Bandit algorithm, and also doing an example of a Bandit algorithm where I give you the actions and the rewards, and then you have to update the value of Q.